At this point, I'd like to introduce Diego, David, and Mao, who will be presenting Breaking the Paradigm of Traffic Engineering Automation. All of these folks work at Nokia, mostly supporting network automation products. They're coming at us today from California, Ottawa, and Texas, respectively. This is Diego and David's first time presenting at NANOG, and it's a pleasure to have them speaking with us today. Welcome, David and Diego and David. And this is Mo's sixth time presenting at NANOG. His first talk at NANOG was called The Power of Kubernetes CRDs, and that was at NANOG 85 in Montreal in 22. We'd like to welcome back Mao as well. Thank you, guys.
Thank you.
Well, thank you very much. I'm going to introduce myself and then I'm going to pass this for the rest of the guys. For who was yesterday, this is the second part of the presentation. Now we are going to go a little more advanced regarding the closed loop automation for this. And we are going to show an application that could be like some sort of out-of-box solution, thinking about it. Maybe PCE cannot give me everything that I need for what I'm looking for to control the traffic in my network, and I can maybe use APIs and put a little more intelligence, in the process. I am Mao. I'm working in network automation in Nokia as a regional PLM. Then Diego, please.
I'm Diego. I also work for Nokia, as people were saying. I'm in the product management team, and I work with everything related to MPLS, segment routing V6 technologies.
And I'm David Watkinson, also in product management, but this time on the NSP platform, working mostly with the path computation engine.
Okay, thank you. Then, as I told, we are going to show a demo at the end of the presentation. Hopefully, we are not going to run out of time, then I'm going to try to be fast. When I started with this presentation and doing this demo, I've been working with transport only 2 years. Then this is my backup here, for any question that you can have about that. And without that, I couldn't actually even start it. And then I appreciate your help, guys. Thank you very much. This is the agenda. We are gonna, well, Diego is gonna bring an introduction of an overview, quick overview we did yesterday. Then we're gonna go to talk a little more about closed loop automation with Dave, and then I'm gonna go directly to the lab.
Thanks, Mao. So as Mao was saying, so what the problem that we have seen lately, or with the years, is that in the beginning with traffic engineering, in particular with RSVP, or either these days with segment routing TE, traffic engineering was normally usually a great solution to solve issues or to be used when we had static or known traffic demands, right? But when we started to see that most operators will have more dynamic demands, related to different applications running on the network or requirements that this application may impose to the network. So we started to see some issues with particularly load balancing, or also with LSP placement and bandwidth utilization across different links or across different nodes in the network. So what we are going to be showing today in this demo with Mao and Dave is how can we use multiple LSPs, or basically multiple LSPs or parallel LSPs, in order to be able to do a load balancing across multiple LSPs, and also provide the good old advantages that we have with traffic engineering, with resiliency and protection using fast reroute and end-to-end protection, right? So another issue that we have had in the past with traffic engineering is that in most cases one wouldn't have the ability to automatically or dynamically create LSPs, considering the bandwidth demands that we may have at any point in time in the network. Okay, so nowadays, we have seen implementations out there giving operators the possibility to use, well, it's not an extension to RSVP because it doesn't extend the protocol per se, right? But we mentioned this yesterday, is that we have seen implementations giving operators the opportunity to dynamically create and delete LSPs, considering bandwidth demands, based on, well, using auto bandwidth and using, a local implementation mechanism to delete and create, or to create and delete these LSPs, and to actually do ECMP among a number of LSPs, right? So this depends on, this is in implementations we have seen, this is configurable. You can do that. You can configure the number of LSPs that you can create, or sub-LSPs that you can create, or member LSPs, also known as member LSPs, that you can instantiate basing on uplinks that you may have, or uplinks that you may have in any given node, or even considering the diverse paths that you may have in the network that may use different links and different nodes, okay? So, and this is applicable to both RSVP and SRT, even it has the potential to be applicable for both cases, right? So for several, for SRT, for RSVP-TE, even segment routing V6, although it will be more difficult to do this using distributed path computation mechanisms when we will want to use segment routing, for example, considering that we don't have any signaling mechanism, and considering that every node in the network is not tracking bandwidth availability on a per link basis across the network, okay? So what we will be showing today is a solution, as Mao was mentioning, using a centralized path computation element, or centralized path computation, or PCE, right? Which is going to be computing these paths and placing these LSPs across resources in the network, right? So just a comparison between the current options that we have today. So using a PCE, we can either use RSVP-TE or we can use segment routing TE. With solutions, as I was saying before, with solutions with using distributed path computation, it might be more difficult if we would want to use SRT, because we don't have a bandwidth reservation or signaling, a signaling mechanism to reserve bandwidth across multiple links. So it might be challenging to do this in a solution out of a box, right? So with a path computation element, we can also have the possibility to compute disjoint LSPs, not only for LSPs that are initiated or instantiated in a specific node, but also for LSPs that might be instantiated in different nodes, because a PCE has a full view of the topology, and a PCE may know how much bandwidth any given LSP is consuming almost in real time, and also knows how much bandwidth utilization on a per layer 3 interface we might be consuming at any given time. So a PCE has this full visibility that enables an operator to compute paths that are completely disjoint, even though if they are instantiated in different nodes, particularly for services that require dual homing or that have dual homing requirements, okay? So this is very difficult to do in a router, because a router doesn't have visibility of all the LSPs that we may have in the network, and particularly if we use a segment routing TE, they also don't know how much bandwidth we have available on any given link, okay? So resource allocation, the idea also with a PCE, taking advantage of the fact that the PCE has full visibility of the network, is to better place these LSPs, considering, for example, the bandwidth required by any given LSP, and also the placement of these LSPs in a network, okay? So with a PCE, we can have this full visibility and optimize LSPs, and considering where other LSPs are placed and how much bandwidth those LSPs are consuming, with the objective of having a more balanced bandwidth utilization across the network. Very difficult to do with a single or with a router or with distributed path computation, right? So, of course, another nice advantage that we have with a centralized path computation is visibility, right? So we have the possibility to have most PCs that you will see out there in the market. They all have nice GUIs to see how these LSPs are being placed in the network. But you can also use IETF based APIs in order to pull that information from the PCE. And if you have a homegrown application to display these paths or to visualize the topology of your network, you can also do that. And also what we have available with a centralized path computation element is the possibility of using multiple triggers to optimize LSPs. And one of those triggers might be bandwidth utilization on a given link. When we reach a specific bandwidth utilization, maybe per link or a global value in a given network, we can instruct the PCE to optimize those LSPs in order to avoid congested links, right? So this is basically what we are going to be doing today. And with that, I would just give the floor to Dave. Thank you. Thanks, Dave.
So bringing all this together and prepare for the demo, talk about a few topics that we're going to be covering in this. So first of all, demo was looked at both PCE init and PCC init LSPs. PCE init is ones where the LSP is configured on the PCE itself and deployed to the nodes via the PCEP protocol. So with PCEP initiate messages. PCC initiate instantiates it on the node itself and uses stateful messaging with PCEP to delegate control to the PCE. So with this demo, we're going to be mostly showing PCC init, but it's also available for PCE init as well. So here's an example, in this case with Open Daylight, of an example of a PCE initiated path. This is one standard around doing that. And following one is an IETF one, which we talked about in the previous session for configuring the PCC initiated paths. And here in the red box, we show the use path computation as true in order to initiate the delegation to the PCE with this LSP. Otherwise, it's basically the same as any other LSP in your network. So returning to closed loop automation, some of the advanced features that we're going to be talking about here can be built into the PC or can be built using automation tools, as we'll be showing in the following demo. Some things to keep in mind, though, I'll be covering through this. So the example I'll be using here is a 5G backhaul network. In these kind of networks, traffic moves around quite a bit as phones roam around through the network. Traffic increases in certain parts of the network at various points of time, and we see a lot of volatility in the traffic in current networks we're involved with. And as a result of that, we've had a lot of customers asking for better control on the backhaul traffic for 5G. So the PCE provides that by managing the traffic on the LSPs and moving traffic around by rerouting them on less congested paths, but it can also handle things by creating new paths in the network, and that's what we're going to be showing as part of the demo coming up. So there's a few things you need to watch out for this. You can do this with a standard stateful PCE, but the issues with it is the reactivity times will vary with this. You won't have necessarily up-to-date utilization information, up-to-date latency information. With this, you're going to be doing this simply off of configured bandwidths in your network, and this can introduce some unusual behaviors with flip-flopping in your network of LSPs moving back and forth. But instead, you can bring in a full closed-loop automation system with telemetry. So you basically learn the utilization information, learn the latency information in your network, and then you can make the best choices for balancing the LSPs in your network to do that. So the important parts of this is you need to handle it in a paced manner so that you don't overwhelm the network. So you do things like de-emphasizing minor fluctuations. So this means small changes in bandwidth or small changes in latency you ignore. So you basically avoid the minor adjustments in your movement of the LSPs that could be occurring way too often in the network. You only want to do it on larger changes. And as well, you need to properly tune your timers for this. So you don't want to be doing things too quickly after an event because it may be a small spike that you're dealing with. So there's a bunch of things that you need to do to manage this in a large-scale network. So move on, and I'll pass it off now to Mao to start in on the demo. Thank you. And give you guys time for beer later on.
Then here you see the Python application that is pulling data, telemetry information from the network. In this case, I'm using Kafka. But also that can happen directly through GNMI using, for example, GNMI-C. And you pull this information about the bandwidth of the path. And based on that information, you can start adding or removing LSP from this ECMP group. Okay. And also I'm using the same application to create policies and constraints on the PCE. This is an example. This is a screenshot of the PCE that is, sorry, this is a screenshot from the telemetry subscription. And I had to enable the stats. I didn't want to put the junk that we have in Nokia, but I couldn't find a way to put it in IETF. But here I have a way that I can enable the stats for those paths, and based on that information, the information that I'm pulling for that subscription that I have with Kafka, I can start adding or removing clones from the LSPs. For the demo, there is a repo. You can go and see more in detail. The code it's a very minimal code in order to make this demo. If you want to fork it and start extending this for any other use cases that you have with your network, please be my guest. But this is for education purposes. Please don't blame me if you start playing around and having issues with your network. And this is only inventive way that we did in Python to call the APIs from the PC, to call the APIs from a LSP configurator. I'm gonna show something with Open Daylight. I'm gonna show something with Nornir too, like other examples that the way that you can do exactly the same thing. You don't need to rely on a specific solution. Actually, this is the reason that because we are using IETF-TE jam models, because it's very open, and you can have it, for example, also in Open Daylight. Then the way that is working is very simple. You have the PCE controller that is pulling all the topology information. Then we are relying a lot on the PCE for path calculation, do all the routes for the paths. And I'm pulling the telemetry using Kafka. Kafka is a very known solution, open source solution for that. And you also have other things like Prometheus, but in this case, I'm using Kafka because it was what I had at that moment. And adding, removing the LSPs using this IETF-TE jam model, and I'm adding the policies also through REST. I'm using a YAML file for my configs because I'm a fan of Kubernetes, and every time that I'm doing something for an application, I'm thinking, oh, well, I want to containerize that and then use it in Kubernetes, and even use CRDs later, to start playing around. It's much easier to onboard that later. How it's working? Well, I told that I think many times. This is in a group of ECMP group. Then I'm adding more LSPs in the same group because I'm seeing that the bandwidth actually is going to a limit, and I'm not putting any special weight on the path. Everything is evenly distributed, and I'm using my application to create the policies, also the constraints. I'm going to show a little more about that. The closed loop is coming from the telemetry information that I'm pulling from Kafka, and then through the LSP configurator, I'm creating the adding clones or removing clones for the group. And I'm using, of course, Containerlab. If you don't know, Containerlab is a solution that you can declare that you can set up a topology file, and Containerlab is going to take that information and it's going to create a full experience of lab. You can have multiple vendors. It's relying on container images, then don't think about virtual servers. And some of the virtual servers can be wrapped inside a container. There are cases like this. And you can also define the way that everything is going to be linked. If you're not aware of the project or you're not following the project, now we have a very beautiful way to show a visual way to see the topology now in Containerlab. Then you just need to put it and it's going to come up in a specific port in the server. A quick view of the topology file. In this case, I'm using CRS because I'm more familiar with it. But you can use any sort of router. And there you can see all the links and the way that I'm defining my topology here. I've just put 8 routers. And I'm using router 1 as my source router for my paths. And I'm going pretty fast because I know that maybe there are people is 30 and they want to grab a beer. Then we have 8 routers, just one level of ISIS. Everything is RSVP, but you can also use a segment routing. I'm connecting my controller directly to the router 1, and I'm pulling the topology information directly from there. And the components of my lab, like I told you, I have Kafka for telemetry to pull information. Then I have a subscription with Kafka. I'm gonna bring a little more information about that. I have my PCE controller pulling the topology information through BGP-LS, and I'm delegating also everything is PCC initiated. Then you have information of the path directly on the devices, but they are delegating the path calculation directly on the PCE through PCE. I'm using also an LSP configurator through RESTconf with an open YAML model. And I'm using YAML file for the configuration of my application and templates in JSON because you can modify the way that the LSPs are going to be created using just a JSON. You don't need to go and touch the code every time that you need to do that. And my lab components, well, I have Python. I'm going to bring a little more information about the modules and the way that is constructed. My configuration management is I'm using NSP, but I'm emulating the IETF-TE YAML model directly from that. It has a northbound. Then you can do the same with OpenDaylight. And then I have my Containerlab. The telemetry is being pulled from Kafka, but Kafka is an open source. You can use it with any other sort of application too. And the PC controller is going to be very hard to replace, to be honest. You can use OpenDaylight, but I'm not familiar with OpenDaylight, and I'm using NSP. But I don't feel that besides OpenDaylight, I didn't find any other PCE controller that could be open source for that. Apache, if you're not familiar with Apache Kafka, is a solution that is decoupling the sources and destinations. Then in many of the applications, for example, you can have this in Kubernetes in many instances. And you can use this to decouple the source or the producer of the information and the consumer of the information. And it's very scalable. And then when your application needs to share some information or like a telemetry or events, you can just put that information in Kafka and forget about it and let Kafka to deal with all the consumers of that information. And then the way that is working is you can define many brokers. Brokers can be, for example, instances of cloud-native instances running in different nodes in a Kubernetes cluster. Then it's going to be resilient to any hardware failure. The information can be replicated. The topics, one topic is, for example, is I'm doing a telemetry subscription. That could be one topic with the specific contours that I need, for example, in this case, like the bandwidth of the LSP. But you can have other topics related to events, internal events and external events. And you can use Kafka internally to share information between your different modules of your application inside the Kubernetes cluster, or you can use it also to share information externally with with like in this case. The brokers can replicate topics between them. Like I'm telling you, they can be distributed in different nodes. And you have the producer that it can use any of the broker to start sharing the information. The consumer that can start pulling information from any of the broker too. This is an example of how when you're pulling information, the format that Kafka is presenting, you have a timestamp, you have the contours, and you have the identity of the object that you're getting for the telemetry. In the case of the PCE, well, I'm putting a very high-level architecture design for that. Most of the time, you have the path computation engine that is the one doing all the path calculation, and you have a graph database. Graph database, I think, is the state of the art for any sort of topology because you have nodes and relations, and it's very optimized for that, right?
Yeah, that's correct. Yeah.
Perfect. And then and you have the router, that is a virtual image, can be in a container or a virtual server, and that is pulling the information. Then most of the vendors, we're using an actual router to pull that information. And this is the actual controller that is doing the delegation of the path calculation and also pulling the topology through BGP-LS. And those have APIs that you can use to create the policies. And in this case, my policies are in a JSON file that you can modify at any moment. Those are the constraints that I'm using, but you can modify those directly on the JSON file that you have here. I'm going to show an example later. But I'm putting some sort of disjoint between the paths. I'm sorting out everything in couples to always be sure that if 50% of the path, they are not going to overlay the same route with the other 50% of the paths. But you can mix different policies. For example, I'm using a proprietary policy here from Nokia that is called Starkweight, but many PCs that they have from vendors, they have their own algorithms versus the standard constraints that you can use for to calculate the paths of the LSPs. And then this is my template to define the policies in the PCE controller. In this case, I can change the name or I can change the ID for my policies. And then when I created my path and I need to link my path to delegate the path calculation to the PCE, I can use the ID of that inside the configuration of the path. Well, here is, I started to decide, okay, what kind of LSP configurator can I have in the market in order to start managing the clones for my LSPs? And then I've been doing other sessions here in Nano talking about, for example, about PyGNMI. Then I don't need an actual SDN controller to go and start creating or modifying paths in my network. I can use a PyGNMI, import that module directly on my Python application and start using GNMI directly on my devices, or netconf, or Nornir. Nornir is going to give me a little more abstraction of that, and it's going to save me a lot of lines of code. Or you can use SDN. SDN could be maybe a little more efficient if you had a bigger network with many devices, with more complexity. And for that, you can use OpenDaylight. That is an open source. And in this case, I'm using Nokia NSP, but I'm going to show some examples also with OpenDaylight that showing you a glance of the way that you can implement that with Python. Or you can invoke also an external application. I did also another, I remember that I did a presentation talking about GNMIC. I use code templates. Like it's not an automation framework, but it could be something that can be very helpful. If you are tired of Ansible, like I said yesterday, you can try this. I tried to do like some sort of comparison between the different technologies. I'm not going to go and read the whole table, but for example, if you are using PyGNMI, the problem is you're going to be tied to only work with devices that support GNMI. In the case of Nornir, you can have other options like SSH or netconf. And if you're using the SDN probably is going to depend on the plugins that you can provide directly there. Other thing that maybe could be important to see is the scalability. When you have PyGNMI, you need to go to every device in the network. Maybe you can have some issues here with the scalability. The SDN maybe is going to sort this out in a better way. Other important thing is the learning curve. If you're using PyGNMI, you have tons of information in the online that you can rely for any issue that you can have. You can even use ChatGPT to get a piece of the code that you need for your application. It's pretty easy. But when you go to for example, or the same for Norner. Norner have a very strong community behind that can help you with any support. But when you go with SDN, actually, I got some. It wasn't easy for me to get information about OpenDaylight, or was a little dated sometimes. And then in the case of NSP, the problem is because it's coming from a vendor, probably it's not that open like in the case of PyGNMI or Norner. Okay. Also, I would say the security. Well, you can use in the case of PyGNMI, you can use certificates if you want to encrypt the traffic. And regarding the deployment, yeah, the learning curve also I think is going to be very hard with SDN because you need to understand almost most of the settings that you need to do on SDN, and sometimes it's not the same way that it's with PyGNMI that you need to just go and set like 2 or 3 parameters, and then it's going to work right away. In the case of this SDN, it's going to be way more complex. Okay. For example, in the case of Norner, I could just import the module. Norner is pretty friendly with Python, and start using defining some of the functions. And then in Norner, you need to define a configuration file, like you need your inventory, you need to define how many threads you're going to run on the devices at once, or the level of the login that you're going to have, what kind of debug level you want, if you want to go deeper, or what is happening in everything that you're doing on the network. Then, as you can see, you need to define the host, that is the inventory, and define groups. When you have common variables between, for example, different vendors, they could be different groups in your file, and they can have different parameters for that. And you can define also default values. And it's very straightforward to just go and create a function for that. You need to initiate Norner using your configuration file, and then you can go and define a JSON file with all the settings that you need from your LSP, and use this function to start creating the LSPs that you need. Okay. This is an example of, for example, of the JSON file that you can use for that function. In the case of OpenDaylight, it's even more easy because you just need the request, or in this case, I added a way to import JSON because I can put all my variables directly in JSON files. I don't need to touch the code after if I want to make a change of the way that I'm going to set in everything on the LSPs. And then with the request, you just need the endpoint of the API, some of the header, and then you're done. You just need to go and start, doing your functions, and you can do your post operation if you want to add something, or delete operations if you want to delete something, or put operations in with your APIs if you want to just do an update. And then this is an example of you can use the same Django model from what I could research in OpenDaylight, the same that I'm using in this case with NSP. Okay. Then, but I have to go with something that I have more experience, and then I chose NSP, but I'm using the same IETF-TE Django that I could use, for example, with OpenDaylight. Okay. Then this solution should work with any sort of solution that is bringing the same standard interface for RESTconf. And for my lab, I have my NSP in a standalone Kubernetes cluster. I put my Containerlab with the topology of the network in another server. And I'm running the application in my laptop because I was a little lazy, and every time that the VPN, I lost the VPN, I have to go and reconnect everything, then it was better just to keep it local. I created my own Python environment. If you're not familiar with that, you can create many applications of Python in different folders. You just need to create your own virtual environment in any of the folders, and then you can use a specific library for that. Then you're not going to have a conflict between one and the other. Don't try to do this directly on your without a virtual environment, or maybe you can screw your laptop or any further application that you're going to do later. Okay. Then this is with all the 3 commands, you're ready with your virtual environment in your folder. Okay. And then in this case, I'm using those libraries. And I split my application in many different files. I created some classes because that was much easier to read later, and I could reuse the same classes for other applications too. I'm not going to go to the specifics, but you can, in this case, what I'm using is a JSON file with my input to do any of the changes in my PCE, for example, for the policies. And I did the same for to clone my LSPs or remove the clones of my LSPs. You see, I'm reusing almost some of the classes that I created before. And then and I split this in different files. If you see, I'm just using, the only library almost that I'm using here is request. The rest are just classes that I made up directly on the files. And why I'm using YAML? Well, like I told you, I'm a big fan of Kubernetes. And then I don't like to touch my code every time that I need to do a change. Then it's much easier if you put a source of truth in YAML for the configuration of my application. But if I want to onboard this application in Kubernetes, also make the things way easier, I could create a config map and put the configuration file. But today, everybody is trying to go to customer resource definitions and to extend those definitions directly through Kubernetes APIs. Then if you are going to do an application, I recommend you to start working with YAML for the configuration of your apps, and that is going to make it easy later to containerize that and put it, for example, in Kubernetes and connect GitHubs or any sort of a CI/CD, practice. And in the way this is working, you go directly to the Kubernetes API. You modify those CRDs that were your former YAML variables, and the operators can go and gently start updating your application, the state of your application with the desired state of your new settings. Okay. To test that, I just did a very simple LSP ping. And I'm trying to put it the size of the ping in order to control how much bandwidth I was using for, in the case of this demo. And now demo time. This is the input file that I'm using. It's very simple. I'm putting the prefix of all my LSPs. I'm defining my PCC initiated path template with all the settings that I need for my LSP. This is IETF Young model, remember? I have my profile ID that is connecting my PCE policies with the delegation of my PCC initiated paths in the devices. I'm using, in this case, I define only 2 LSPs as my minimal amount of LSPs in the group, but I can put more. I define my group ID to force this link strict disjoin policy between couples, and starting from the 60 because I didn't want to have a conflict with the others group that are defined inside the PCE. And I also put my topic where I'm pulling information of the telemetry from Kafka, my Bootstrap server where the Kafka is, I can start pulling information. And I put a certificate. That is the way that Kafka is giving me the authorization to go and pull information. Okay. And then after I start running this application, depending on what is going to be the trigger, is I'm going under the limit of my bandwidth, it's going to start removing the clones. If I go over the limit, it's going to start adding more clones. And the way that I'm controlling that, and I like that because it's giving you a very easy way to go. And this is why I was telling you, putting this in a YAML file, I don't need to go directly to the application and change my code in order to make this different. In the YAML file, I can control what is going to be my period for going and checking the occurrences of the bandwidth or the telemetry information, and start checking how many occurrences I have when it's going over the limit. In this case, my up threshold is defining my maximum bandwidth that I'm putting has a limit. And if I have 2 occurrences that are going over that limit, it's going to trigger a clone. Okay. If I put my also my down threshold, if I go under that, and I put 4 times, I've been checking about use cases. Sometimes it's better even to put more occurrences when it's going down, because sometimes the traffic can have, just a spike down, going down, surprisingly, and then going up again. You don't have control of the traffic. Then it's always easier to add than remove LSPs in the ECMP group that you have in the router. Then I'm using this template to set up everything in my LSPs. This is the template, the actual template that I'm using, and defining just the name. But I'm also changing the ID to link my PCE policies in the PCE, and I put an extended ID with the group ID to force this joint policy between the couples. Then if you go to the PCE controller, you're going to see, I'm going to show that in a video later, but you're going to see the profile ID, and this is going to be referenced directly from the configuration of my path. And this is going to be the actual format that I'm using for the path based on the prefix that I define in my YAML file. And then the idea of putting this in couples is I'm forcing to, for every 2 paths I'm creating, I'm forcing that they need to be they need to be disjoint. They need to go through different routes. And I'm now going to show the way that I'm creating a policy directly in my PCE. Then I put my Python application as just a command line interface for now to make it easy. And then and you can see that I can go directly to my JSON template of my PCE policy, and I can override information like the name of my policy and the ID of my policy. And now I have a new policy for my PCE that I can use for all my LSPs. And I can define different constraints and objectives for my policy. And I also have the option to delete it if I want. And to start this, my application, I just need to go and define what is going to be my YAML file as input for that. And as you can see that this is my telemetry information. Then I'm going to create a new, I have a subscription already for my LSP stats. I need just to have the same topic ID in my YAML file, and using that is going to go and start pulling telemetry information for that path. And with some of the other elements, I'm writing some of the settings on my templates to create the LSPs. And now it started to pull information from Kafka. Then the way that it's working is going in every minute is checking how many occurrences that I'm having, if I'm going over the threshold or down the threshold that I define for this. And depending on that, it's going to trigger the creation of a new clone or remove the clone of my ECMP group. Then in this case, I have 2 occurrences to create, the path. And then when I start with the LSP ping, I'm going to try to take the LSP over the limit. And then you see that it's actually going over the threshold that I find for my up limit. And if I have more than 2 occurrences, I'm going to forward this. and you see now I've created one path, and probably it's going to create another one. No, it's going to create another one. Actually, I saw it. And because I'm still going over the threshold with 2 occurrences per every period of time. And then now I have 2 new paths that are in the same CMP group, and there are actually those 2 paths, they're not overlapping in the same route because they are actually in the same group ID. And you can see that they created another one, still over the threshold. Okay. And the same is going to happen if I see that I'm going under the threshold of my bandwidth, but in this case I set up 4 occurrences, and it's going to delete the clone. Then I go back to the same state. Already deleted one of the paths, and you see now is because it's going under the threshold, it's going to start deleting more and more paths. And then with this, the idea to show this is, okay, you can have the PCE, you can have the telemetry option, in your PCE, but the PCE is not going to start creating more paths or removing more paths. You need something else to do that. And then in this case, what I did is I created that through a Python application that's also pulling the information of the telemetry. Okay. Then we are almost done. Wait, just 1 minute. Well, the idea of this demo is we did this in just one presentation, but the people here in Nano, they forced us to split it in 2. You're lucky because that could be 2 hours here in this stage. And then we split it in 2 because we wanted to show you first, yesterday we showed you all the standards that we have for traffic engineering and the things that are not also standards, some that are proprietary solutions or technologies. But the idea is to show you a different way how you can control the traffic or the LSPs in your network. But you still can rely on the PCE to calculate all the paths, to distribute the performance. The problem is the PCE is not going to create more paths. And the idea is I don't want to have that person just going and checking, how bandwidth I have, in my path to start going and creating more paths and removing more paths. You can scale this, of course. You can scale this to work with more routers, with a bigger network. But I'm going to leave that up to you if you want to fork the project and start playing around with it. Some additional resources. If you want to understand a little more about GNMIC or Containerlab, there are really good presentations in Nanoc. We use a lot of the information from pusher packers to try to go over the tutorial of the PCE. And you can go and check the repo. Please, it's still work in progress. If you see something you don't like, let me know and can help you or update that documentation in the repo. Thank you.